video, we will be looking at how to create a one-sample t-test for the mean. We already did one of those. And in those cases, we actually knew what the population standard deviation was, sigma. And then you run what we call a t-test. And then you use as your test statistic z equals x bar minus mu over the standard deviation of the square root of n. And what if you don't know what sigma is? What if you don't know what the population standard deviation actually is? So the question came up, and we could just use the sample standard deviation, which is as simple as S, as an approximation for sigma. So then the question came, what is the distribution of t equals x bar minus mu over S of the square root of n? Is it actually normal, since the z was normal? And that looks like the same formula. But actually, no. So the question came up, what was it? So a man by the name of W.S. Gossett came up with this. And he figured out that the distribution is, and he called it the student's t distribution. There are some conditions that must be made for the formula to be a student's t distribution. These will be outlined later. It's called the student's t distribution because he couldn't name it under his name because of the rules of the company he worked for. It had nothing to do with only students using it. It's used by everybody. So we have this distribution. It has what we call n minus 1 degrees of freedom. The explanation for that is the standard deviation formula has that n minus 1 in there. This is the same as the standard deviation. And you can kind of think of it as if it's your freedom of choice. So the first n minus 1 data values, you have freedom of choosing what they are, but the nth data value has to be a certain number because they have to add up to, you have to get those deviations to add to 0. Another thing to think of it is you have 5 people who want something. 5 of them, the first person gets 5 choices. The second choice gets 4 choices because the first one took one. The third person gets 3 choices because the fourth person took some. And so forth down to the last person actually gets no choice because there's only one thing left. So they actually have no freedom of choice. And that's kind of what this is about. There are many t distributions, one for every different degrees of freedom. So this is what the graph looks like for when your degrees of freedom is, this is a normal distribution. This is when your degrees of freedom is 10. It looks a lot like the normal distribution, but if you click on it, you notice that the shape changes ever so slightly. And even when degrees of freedom is 2, it gets even narrower. So it keeps getting narrower, and the ends are not as flat. So that's how it kind of changes. So now we're going to use this to test the parameter. And that means you have to use the student's t distribution to find your probabilities. I'm not going to go through all the steps. We're going to do an example of this, but basically you got your hypothesis test. You got the same 6 steps you got for every hypothesis test. The conditions for this test is you have to have a random sample of size n is taken, and the population of the random variable is normally distributed. The one thing I will mention is the t-test is fairly robust to this condition if your sample size is large. So if it's not met, you could just take a larger sample, and then your t-test is valid. All right, so we're going to go through how to do this. We'll get through how to process it when we do an example. So here's our example. The Kyoto Protocol was signed in 1997 and requires countries to start reducing their carbon emissions. The protocol became enforceable in February 2005. So in 2004, the mean CO2 emission was 4.87 metric tons per capita. A data set contains the random sample of CO2 emissions in 2010 was taken. CO2 is emissions is measured in metric tons per capita. So this was retrieved from a data set, and what we want to know is there enough evidence to show that the mean CO2 emission is different in 2010 than in 2004. And we're going to test this at the 1% level. So our first step is to, of course, always state your random variable and your parameter. So our random variable in this case is your emission level, or your CO2 emission level, I should say. in 2010, because we know what it was in 2004. We weren't measuring that. We were measuring it in 2010. That's your random variable. Your parameter in this case, because you've got numerical number, would be your mean CO2 measures, emission level. Again, in 2010. So now we get to our hypothesis. So we have two hypotheses. You have the null hypothesis, which you can call HO, and you have the alternative hypothesis, which you can call HA, or you can just call it alternative and so forth. Let's spell it correctly. Also make it capital. All right. So this is, I usually start with the alternative hypothesis. This is actually what your HA is. This is your question you're asking. So the question we're asking, is there enough evidence to show that the mean CO2 emission is different in 2010 than in 2004? So I can actually just copy that sentence and put it in here as my HA. That's my question. That's what I want to look at. That's my alternative hypothesis. My HO then is always equal to. So it's not that they're different, it's the same in 2010 as in 2004. Now we will need to know what the number was in 2004. It was 4.87. So let's just copy that and put that down here so that we have that information to go with, because we will be using that. All right. So now we get to our conditions. And the conditions are, first, that you have a random sample of, and I don't know how many, but let's see if we can have over here. I thought I ran this, so let's run this again. There's my emission level. Okay. So I have 249 observations. So there are a random sample of 249 observations. So random sample of 249 CO2 emission levels was taken. That is what we're stating. So let's actually just state that. That's what we want to have happen. Our check is to see, did it actually happen? Well, unfortunately, I don't know how they took the data. I don't know where this came from. I don't know how this data was collected. I don't, oh, wait, it does say a random sample is from a random sample. So we do actually know what this is. That's good. It's always nice to go check that. So this was stated in the problem. It's not always stated in the problem, so don't just automatically assume it is. Sometimes it's not stated and you have to say you don't know. Sometimes it describes the process. Sometimes you are taking your own sample and you have to figure out how to make sure it's a random sample. So don't just always say it's stated in the problem, because it may not be. Your second one is that the distribution of the CO2, the random variable, is normally distributed. Well, to answer that, we have to actually look at the density plot and the normal quantile plot. So let's insert an R chunk. We are doing a GF density plot. We want to do it. Let's see what the variables are. We are dealing with 2010. So notice there's a Y in front of these, and we've got emission levels in lots of different places, but we want the one in 2010 because that's the year we're interested in. So we do Y 2010, and data set is equal to emission. And then I'll put a title on it, and I'll say emission level, CO2 emission levels, I should say. In 2010. And then I'll probably put a label on the x-axis. Might say something like just CO2 emission levels. And you could put in the units. So the units here were metric tons per capita. and then we can run that. So that definitely does not look like a normal distribution. It looks very skewed. Let's do the quantile plot. So that's GFQQ for quantile. And everything else is going to be exactly the same. So I'm just going to copy this, paste it in here. The only thing I will do is I'm going to take out the XLab. It puts its own XLab in here, and I kind of like that one, so I'm going to take that one out. And then we'll run this again. And that definitely does not look linear. That looks kind of exponential. So looking at the graph, so the check, the normal quantile, let's just go with this one, the density plot does not look normal, look bell-shaped. And the normal quantile plot does not look linear. So the population, the sample, I should say, is probably not from a normal top population, normally distributed population. However, in this case, the sample size was large. So the sample size was above 30, so it's okay. Since the sample was over 30, the t-test is robust and it is okay. I probably wouldn't say okay in a publication, but for right now, I'll just say okay. Now we can get to our calculations. So the calculations, I'm going to get insert an R chunk. We are going to do a t-dot test. We are using Y 2010. Notice I put the tilde in front of it because this is, again, my explanatory variable. My data set is emission. And what I need to tell is what the mu value is. What is the population mean? That's what mu stands for, is the population mean. And this is where I needed it. I put this value in here and the null hypothesis and the alternative hypothesis. That's the 4.87. That's the number I'm comparing it with. I may also have to put the alternative equals, but since this alternative hypothesis is different then, I don't need to worry about the alternative equals. It's a default. It will automatically go to that one. So I run this. Here is my p-value. Here is my test statistic. So my test statistic is negative, which means that 2000, probably 2004 is less than 2010 because we're going to take the, actually, yeah, we're going to take the 2010 value and subtract off the mean of 2004. We get a negative number that tells me it's probably is less, but the p-value is pretty small, is not small enough, so we can't reject HO. So our conclusion here is to fail to reject HO since p-value is greater than 1%. That was my alpha level. This means in my interpretation, there is not enough evidence to support that. And again, this goes back to my question. So let's go back to our HA, our alternative hypothesis. My question was that the mean CO2 was different in 2010 than 2004. So that's what I don't have evidence to support. I don't have enough evidence to support that the mean CO2 emission is different in 2010 than in 2004.